Hello everybody, my name is Emin Skiljan. Today we'll be going over project number 5, question 1. So, what is the phase diagram of your metal A and metal B when they form an alloy? So, our metals in question are aluminum and magnesium. So before we go over the specifics of it, let's go over what a phase diagram is. A phase diagram in physical chemistry, engineering, mineralogy, and material science is a type of chart used to show conditions, including both pressure, temperature, and etc., at which thermodynamically distinct phases, such as solid, liquid, or gaseous states occur and coexist at equilibrium. And on the right, you can see a labeled phase diagram chart going over some temperature and pressure states. So, what the points mean on the diagram. A typical phase diagram, the solid green line shows the behavior of the melting point for most substances. The dotted green line shows the anomalous behavior of water. The red line showed the sublimation temperature, and the blue line the boiling point, showing how they vary with pressure. And on the right, you can see all the labeled points and lines. So, how do metals experience phase changes? Well, in the nature of bonding, metallic bonds involve a sea of delocalized electrons that allow atoms to be held together in a highly organized crystalline lattice. The structure gives metals defined solid, liquid, and sometimes plasma phases in their phase diagrams. Phase transition behavior. In metals, they exhibit well-defined melting and boiling points due to strong metallic bonds. Their phase diagrams often include solid-solid phase transitions, so from one crystalline structure to another, such as body-centered cubic to face-centered cubic, so BCC to FCC. Complexity of solid phases. Metals possess multiple solid phases depending on pressure and temperature. They can also exhibit phenomena like polymorphism, different crystal structures, and allotropy, which is different forms of the same metal, same element. So continued, thermal conductivity and specific heat. Metals have high thermal conductivity and heat capacity due to their free electrons. Phase diagrams reflect sharp, well-defined phase boundaries because temperature spreads evenly through the material. Critical point and supercritical phase. Metals exhibit a high critical point due to strong bonds. The supercritical fluid region is less explored, but typically involves extreme temperatures and pressures. Behavior at extreme conditions. Metals retain structural complexity even under extreme conditions, making their phase diagram richer, and they can also transition into a plasma at very high temperatures. So for aluminum magnesium alloy, this is our phase diagram. If you'd like to pause and look at the specifics of it, you're more than free to do so. So specifics regarding the graph. The diagram consists of several distinct regions representing solid phases, FCC, which corresponds to aluminum-rich solid solutions, HCP, which corresponds to magnesium-rich solid solutions. Intermediate phases like ALMG sub beta, ALMG sub epsilon, and ALMG sub gamma. Solid solubility. Magnesium has limited solubility in aluminum, shown by the narrow region of the FCC phase, and vice versa for aluminum and magnesium. These limits define the terminal solid solutions. Eutectic and peritectic reactions. The aluminum-magnesium system shows various reactions such as eutectic and peritectic transitions. These reactions involve the coexistence of liquid and multiple solid phases. So continued, we have intermediate compounds. Several intermetallic phases, like the ones we just went over, form, which play a significant role in the mechanical properties of aluminum-magnesium alloys. Melting point variations. Pure aluminum melts around 660 degrees Celsius, while magnesium melts right around 650 degrees Celsius. The introduction of magnesium into aluminum or vice versa lowers the melting point in certain regions due to alloying effects. Critical compositions. Specific compositions such as the eutectic point or the solubility limits are vital for alloy design as they provide optimal properties like strength or corrosion resistance. That's the end of the presentation. Hope you learned something new today. Have a great rest of your day.
Before going through the drawing, let's just go through explanations of solidification. So the process of solidification is where a liquid transforms into a solid. This occurs through cooling, where atoms organize into a crystalline structure, forming a solid phase. For example, a freeze, so like an ice cube, water turning into ice. An allotrope, the existence of an element in different structural forms in the same physical state. For example, iron exhibits with different crystal structures and face-centered structures depending on temperature and pressure. So a eutectic reaction is a transformation where a liquid phase cools and simultaneously solidifies into two or more distinct solid phases at a single temperature and composition. For example, looking at L equals alpha plus beta is just a region in this graph where a eutectic reaction takes place. It happens in the liquid phase. Some versions of these reactions are the hypo and hyper. Hypo refers to an alloy composition that is below the eutectic composition. Upon cooling, the alloy first forms one solid phase before reaching the temperature where the reaction occurs. A hyperreaction refers to the alloy composition that is above the eutectic composition. So pretty much the same thing, just above the range. Eutectoid reaction is similar to a eutectic reaction, but involves in the solid phases. A single solid phase transforms into two different solid phases upon cooling. Here's another example, just now in the solid phase. And likewise, we have hypo and hyper. Hypo describes an alloy composition below, while the hyper describes above. Finally, a peritectic reaction is a transformation where a liquid and one solid phase combine upon cooling to form different solid phase. So now we're taking a combination of both. Likewise, we have a hypo and hyper version. A hypo describes a composition that is below the range. Upon cooling, the reaction L plus alpha occurs, but with more alpha forming. And a hyper describes a composition above. Upon cooling, the reaction L plus alpha to beta occurs, but with more liquid this time. And here we are with a summary of tables, given each of the reaction types, a description of what they are, so if you'd like to see them, pause, and the phases involved.
Cooling of aluminum-magnesium alloy. For our first example, we're going to show the cooling of 67.7% magnesium aluminum alloy. We can see in the phase diagram that at 67.7%, it starts from the liquid phase and goes directly into two solid phases. At 600 degrees, we can see on the chart that it is still in the liquid phase, and the liquid microstructure is drawn to the left. At 437 degrees Celsius, we can see that that's when it goes from a liquid phase and transforms into two solid phases. This is called the eutectic point. This gives the eutectic microstructure, which is alternating layers of, in this case, gamma and delta phases. And below, that microstructure is drawn. Our second example is cooling of 80% magnesium aluminum. We can see in the chart to the right that it's at 80, it starts from liquid phase, then goes to a solid and a liquid phase, and then to solid phases. At 600 degrees Celsius, it is in the liquid phase, and the microstructure of it as a liquid is drawn below. At 500 degrees Celsius, we are in the solid and liquid phase. We can see that its microstructure that the solids are drawn in and mixed in with the liquids. The liquid in this microstructure takes up 53.33%, and the solid takes up 46.67%. At 400 degrees Celsius, we are under what we previously talked about, which was the eutectic point. But because we are to the right of that and closer to delta, this will be known as hypereutectic because delta will take up more space within the microstructure. And we can see that when we calculate the percentage of each solid within the microstructure, with gamma taking up only 27.6% and delta taking up 72.4%. And the microstructure is there below.